Hello, scholars. We are now going to talk a little bit about what we call weight-volume relationships, as well as relative density of coarse-grained soils. Now, weight-volume relationships are very important. They're relationships that help engineers understand a little bit about the fundamental properties of a soil, which will in turn help us to have better engineering designs and help us understand a little bit more how the soil is going to behave in certain situations. Now, when it boils down to undesirable engineering behavior, almost all undesirable behavior relates back to the voids. Typically, the more voids a soil has, the more problematic it can be. And so to understand the voids and to understand what's in the voids, engineers are going to use a special type of diagram that we call phase diagrams. Imagine a bucket of soil like we have here shown on the left. If we have soil that's in that bucket, there's going to be three main parts that comprise the soil. We're going to have air in the voids, we're going to have water in the voids, and then the soil particles themselves comprise solids. And so a phase diagram is just an imaginary way of breaking the soil into its three fundamental materials and dividing them up. So imagine if you could magically separate the soil, or if like the Hulk were to come in and smash the soil really hard so that all the solid particles went to the bottom, and then the water sat on top of it, and then the air sat on top of the water. That is a phase diagram. Now, we usually represent phase diagrams in one of two ways. We can represent them with volumes, or we can represent them with weights, usually both. And weights are pretty easy because that's something that we can actually measure in the laboratory. So we can take a sample of soil and weigh it. We can dry it in an oven and weigh it again. And that way we can get the weights of the solids, weights of the water, the total weight. Typically, though, we're going to make a very critical assumption that we have zero weight for the air. And I know that air does have some mass and thus it has some weight, but for engineering purposes, we're just going to neglect it. It's going to make our lives a lot easier if we do. With the phase diagram and with all the information about volumes and weights, we can calculate some very important parameters. For instance, we can calculate the void ratio. We use the letter E to denote void ratio, and this is simply the ratio of the volume of the voids divided by the volume of the solids. Now, the reason why the void ratio is useful is because it gives us an indication of the relative percentage of the soil that is void space. And so the higher the void ratio, typically the more problematic the soil can be. Related to the void ratio is a term called the porosity. This is simply the volume of the voids divided by the total volume. So it's a little different than the void ratio, but still related to it. Next, we have the degree of saturation, which is the volume of the water divided by the volume of the voids. So this is a term that ranges between 0 and 100%, or 0 and 1. So if all of the voids are filled with water, then the degree of saturation equals 1. If there's no water at all in the soil and all of the voids are comprised of air, then the degree of saturation is 0. One thing I do want to go back to and talk about the void ratio. There is a misconception sometimes that students have that the void ratio cannot be greater than 1, and this is not true. The void ratio can be much greater than 1. There is no limitation on the void ratio. And in fact, in my career, I've encountered lots of soils that have a void ratio greater than 1. Recently, in 2016, when we were doing an earthquake reconnaissance in Kumamoto, Japan, there were some soils that demonstrated a lot of deformations and problems. When we look closer at the information and the boring logs from that soil and the laboratory testing, we found that that soil had a void ratio of approximately 6. That means that for every unit volume of solids, there is 6 unit volumes of voids, which might explain why the soil was so problematic in the earthquake. Moving on, when we get to some parameters that relate to weights, we have the moisture content, which is very important and widely used in geotechnical engineering, and that's just the ratio of the weight of the water divided by the weight of the solids. So that ratio is just going to give us an idea of how much water is in the soil in terms of weights. The unit weight of the soil is something that is pretty well known. Unit weight is just going to be the total weight divided by the total volume. In terms of this unit weight, we also call this gamma moist, or sometimes just gamma M for moist unit weight. And so this would be if you just took soil as it is in a field and stuck it into a known volume and weighed it, and you knew that volume, that would be its unit weight. But I'm going to go to the whiteboard here because I want to make some important distinguishment here. Because as geotechnical engineers, we are going to use different unit weights. The unit weight I just described, let's change color. I'm not feeling like a green today. Let's use blue maybe. So the unit weight we just described is the moist unit weight, or just gamma. And like I said, that is the total weight divided by the total volume. Now there's another unit weight, which is the dry unit weight. Dry unit weight is equal to, can you guess? The weight of the solids divided by the total volume. Now, a lot of scholars like to think that it should be the volume of the solids, weight of the solids divided by the volume of the solids. But that's not accounting for the void space. In the dry unit weight, you want to account for the void space. You just want to account for the void space in the condition that there's no water in it. So in this instance, we would say that the degree of saturation is equal to 0%. Another unit weight is called the solid unit weight. And this is the unit weight that you were thinking of before. This is the weight of the solids divided by the volume of the solids. So this is the unit weight of just the soil particles themselves without any void space in it whatsoever. So if you had just a solid brick of soil material with no void space in it, this is what you would have. And the solid unit weight can be calculated in another way. We can multiply it by the specific gravity. Every material has a specific gravity, and we'll talk a little bit about this parameter in just a few minutes. But it's the specific gravity times the unit weight of water. And the unit weight of water is typically known. We typically assume it to be 62.4 pounds per cubic foot, or in metric units, 9.81 kilonewtons per metric meter. So that's an easy way that we can compute that. Finally, we have the unit weight of the water. And this is just equal to the weight of the water divided by the volume of the water. Typically, like I said before, this is a known or assumed value. Oh, I almost forgot. There's one more I want to introduce. We call it the saturated unit weight. This is equal to the total weight divided by the total volume in the instance that the degree of saturation is 100%. So if you think of it kind of like the dry unit weight was a degree of saturation of 0%, this is the opposite of that. This is if the soil is completely saturated, the voids are completely filled with water, and so the degree of saturation is 100%. That's the saturated unit weight, and this is typically the unit weight of soil that we assume beneath the groundwater table. So these are the different unit weights we're going to talk about this semester in class. And the sooner you can familiarize yourself with these and these different definitions, the better off you'll be. Let's go back to the lecture. Similar to a unit weight is a mass density. So this, instead of weight divided by a volume, this is just going to be the mass of the soil divided by its total volume. And then, like I mentioned before, the specific gravity. Specific gravity is a term that relates the mass of a material to the mass of water. And soil is conveniently very predictable. Specific gravity of soil generally ranges between 2.65 to 2.7 if you have a sandy material, and it's around 2.7-ish or so if you have a clay material. And even if we know nothing else about the soil, we can still predict or guess the specific gravity with pretty good confidence. And so if I had to guess anything about the soil, not knowing anything about it, it would be its specific gravity. Now I'm going to introduce two equations to you that are going to be the key to your being able to complete a phase diagram. By completing a phase diagram, I mean that every single one of these weights and every single one of these volumes should have a computed value next to it. Once you compute all those values, you've completed your phase diagram. The weights are typically easy. Students have a pretty easy time filling in the weights because those are usually given to you. The volumes they struggle with a little bit. These two equations that I just showed you and circled are going to be the key to your completing a phase diagram. They're kind of like little tricks. If you can get the volume of the solids using this equation I showed you, and get the volume of the water using this equation above that I showed you, then typically you can complete the rest of the phase diagram. So notice how I'm computing volumes as a function of a weight that we know, as a specific gravity, which we can assume, and then as the unit weight of water, which we typically know as well. Now, one cool little algebraic trick we can do with phase diagrams is we can divide every term in the phase diagram by the volume of solids. So we normalize everything by the volume of solids. So if we do that, then we can come up with some pretty useful relationships. So for example, if I divide the volume of the solids by the volume of the solids, then that's just equal to 1. Well, that's easy. Well, what happens if I divide the volume of voids by the volume of the solids? Well, volume of voids divided by volume of solids is the void ratio. So that's just E. Then, if that's the case, the total volume is just going to be equal to 1 plus E. Then I can, using that relationship, compute, for instance, a relationship for my porosity and relate it back to void ratio. So this is the equation that relates void ratio to porosity. But using this normalized phase diagram, we can come up with some pretty useful relationships. For instance, if I look at the volumes, I can relate the weight of the water. I'm sorry. If I look at the weights, I can relate the weight of the water to the degree of saturation times the void ratio times the unit weight of water. And if I take that relationship, I can manipulate it, and I can solve and develop this very nifty equation here. And I like to remember this equation just by a simple little phrase, structural engineers equal wacky guys or gals. Or you could do any phrase or any term that you want, but this is a way that I remember it. And so I can use this relationship to help me solve for different properties of the soil pretty quickly and easily. Some other very useful relationships we can derive from this phase diagram are circled here. A relationship for the moist unit weight of the soil, and then a relationship that involves the dry unit weight of the soil. So with these three phase relationship equations that I circled here, we can solve for most parameters of the soil that we're interested in. So it's very good to become familiar with at least these three equations. Now there's dozens of other phase relationship equations that can be derived, but I found almost all of them come from one of these three equations right here. So let's just jump right in, and we're going to do an example. What I want you to do is take a few minutes, and I want you to complete a phase diagram. Here's the information that's given to you. We have a soil sample that in its natural state has a volume of 0.33 cubic feet. It weighs 39.93 pounds. Then the oven dry weight, so that's the weight of the soil after we dry it in the oven, is equal to 34.54 pounds. If we assume 2.67 for the specific gravity, calculate all of these different soil parameters: the moisture content, the moist unit weight, the dry unit weight, the void ratio, the porosity, and the degree of saturation. So, if you go down into the description box of this video, there's going to be a link to a blank phase diagram. Go ahead and print that out, or take the electronic copy on your tablet and take a few moments. Use the equations that we talked about before, especially the two key or trick equations for the volumes, and see if you can solve the entire phase diagram here. Now let's go ahead and just fill in the information that we know to give you a head start. We know the total volume is 0.33 cubic feet. We know that the weight of the solids, this was the weight after it came out of the oven, is 34.54 pounds, and we know that the total weight is 39.93 pounds, and we've assumed specific gravity of 2.67. Oh, the other thing we know, of course, is that the weight of the air is 0 pounds. So with this, go ahead, see if you can fill in every one of these blanks. Pause this video, take a few minutes, do the best you can, and then come back on and we'll solve the rest of the phase diagram. Go. Okay, so hopefully you had a chance to take a few minutes to try to solve this phase diagram and practice with this. So let's go ahead and solve the unknowns. The first one is the weight of the water. Well, the weight of the water is simply going to be equal to the total weight minus the weight of the solids, the difference between those two. So I get 5.39 pounds. All right, now let's go over to the volumes. The first volume I'm going to solve is the volume of the solids, and I'm going to use my little trick equation that I gave you in the earlier slide. And I know all of these terms, so all I have to do is plug in the parameters and solve the number. So the number I'm plugging in, 34.54 pounds for the weight of the solids, 2.67 for specific gravity, and 62.4 for the unit weight of water. So I get now a volume for my solids. I'm going to use my other trick equation to solve the volume of water, as you can see right here. So here's my trick equation. So now I have the volume of the solids, I have the volume of the water. All I need is the volume of the air, but I have a total volume. So to solve the volume of the air, I just have to subtract the volume of the water and the volume of the solids from the total volume, and that leaves me with the volume of the air. So using the simple math here, we were able to fill in every blank on the phase diagram. Now with this information, we can go through and we can calculate all of the different parameters that we were asked for. For instance, moisture content, it's the weight of the water divided by the weight of the solids. Well, weight of the water is just 5.39 pounds. So plug that in and we get 15.6% for our moisture content. You can see plugging and chugging for moist unit weight, for dry unit weight. It's very, very easy to solve these parameters once we have the phase diagram. And even if I didn't want to use the phase diagram but use one of my three equations that I presented to you for my phase relationships, I can do that. All I need is my moist unit weight, which I computed right here, and I need my moisture content, which I computed right here. So I just plug in, for instance, 0.156 for my moisture content, and I get 104.7 pounds per cubic foot. Same thing I got just right above it. Void ratio, very easy. I just need the volume of the voids divided by the volume of the solids. All of those things were computed. And then the porosity I can relate back to void ratio once I have it. And I get 0.37, and degree of saturation, I compute 70.6%. So really what you see is using a phase diagram, we're going to get as much basic information about the soil as we can, and then we're going to use the phase diagram to compute and derive all these other parameters that are going to be of interest to us as engineers. Now, we can use phase diagrams to also solve some really more sophisticated or advanced problems like borrow and fill problems. These are problems that are very popular on the Fundamentals of Engineers exam, or the FE exam, and so I always recommend to the students to study with me that they learn these borrow and fill problems very well and become well versed and practiced with them, because they will almost always encounter one of these on the FE exam, and they're also on the professional engineering exam as well. So in this example, I have 8,000 cubic yards of soil to be excavated, and it has a void ratio of 1.2 and is to be placed at a void ratio of 0.8. So what do we know? We know that the volume of the borrow is 8,000 cubic yards. We know that the void ratio of the borrow is 1.20, and the void ratio of the fill is 0.80. So we want to find a couple things. We want to find what the volume of the fill is. We want to know how much water needs to be added to the soil if we want a moisture content of 18% and the moisture content of the borrow is at 15%. So those are interesting problems and things that we have to solve. Now, there's a trick to solving these problems, and engineers can sit and spin their wheels for a long time trying to figure it out, but if you know the little trick, you can solve almost any one of these borrow-fill problems. Now, the borrow and the fill are going to have different volumes because they have different void ratios. We can adjust the amount of voids in the fill because we can compact it. And we will also have different water contents because we can add or take away water. But there's one thing that will always remain constant between the borrow and the fill. And that thing that will always remain constant is the solids, the volume of the solids and the weight of the solids. Those will always remain constant between the borrow and the fill. So we can use that information to go ahead and build a relationship that relates the total volume of the fill to the total volume of the borrow. And then we can solve for the volume of the fill. I'd like you to pause this presentation and look at the equations and the relationships that I related here in these different steps. See how I went through, I solved for a couple of key equations, and then I took those equations, related them both to the borrow and the fill, and then when I got to the weight of the solids, I set the weight of the solids of the fill equal to the weight of the solids of the borrow, and that's always the key with these fill and borrow problems. If you can do that, then you can solve for whatever you need to. So take a moment, step through these equations, and see if you can understand what I did. For part B, what we need to do is use the relationship for moisture content to solve for the weight of the water. So again, I'm solving a relationship for the moisture content, and I'm going to relate that back to the weight of the solid. So this right here is my key equation. And then I'm going to go ahead and use my key assumptions, put these things together, and I'm going to find the difference between the weight of the water in the fill and the weight of the water in the borrow. That difference is how much water needs to be added to the soil to achieve my target moisture content of 18%. So I'm not going to spend time going through these derivations and equations in detail. But pause, take a moment, and see if you can understand what I did. And again, see how I'm using some of the basic phase relationship equations, perhaps modified a little bit, but I'm using them to get what we need to solve what was asked for in the problem. Okay, last thing I want to talk about in this lecture is relative density, and we're changing gears quite a bit, but it's important to understand a little bit about relative density. Relative density is a term that we use to indicate the in situ density of coarse-grained soils. Now, so relative density only applies to coarse-grained soils. It does not apply to fine-grained soils at all. So we're only talking about sands and gravels when we say relative density. So imagine if I had a pile of sand, and these little yellow balls represent the particles of that sand. If I were to stack those sand particles in the loosest possible configuration, meaning that the void space was the biggest it could possibly be, you could see that this configuration right here would be the loosest I could make that soil while still having the soil particles touching one another. Because that's the loosest configuration, we know a couple of things. We know that the void ratio is the maximum void ratio it could possibly be for this soil. Because it's the maximum void ratio, we're going to say the relative density of this soil in this state is 0%. That's the loosest we can make the soil. Conversely, if I take my little sand and I say, let's make those balls as tight as we possibly can and still have the balls touching, if I make those balls, those sand particles, as close as I can without breaking them, then you can see that here on the right, this is the densest possible configuration, meaning that the void space in between those particles is as small as it can possibly be. If that's the case, then we say that this is the minimum void ratio possible with this soil, and then this is the highest possible relative density, or a relative density of 100%. So anything else I do with this particular soil is going to fall between one of these two conditions. It's either going to be more dense than the loosest possible configuration and more loose than the densest possible configuration. So the actual relative density of any soil is going to be between 0% and 100%. So that's why we call it relative density. It's relative to the loosest and the densest possible configurations of the soil. Now, most soils in the field are going to be between 30 to maybe 70 or 80% relative density. If we want to get a soil above 80% relative density, we usually have to do that manually with compaction equipment. Conversely, if we want soil to be looser than about 30% relative density, which we never would want that, we would have to do that ourselves, usually by placing the soil with hydraulic fill or something that's going to really allow the soil particles to settle and configure themselves in a very loose configuration. So how do we compute relative density? Well, it's just simply a ratio. It's a ratio of what our actual void ratio is to what the range of the maximum and the minimum void ratio is. So it's real easy to compute. If we don't have void ratios and we have instead unit weights, we can use the unit weights as well. We're going to use dry unit weight for it, however. And so you can use either of these two equations to compute the relative density. So remember a couple things. It's only applicable to coarse-grained soils. It's not applicable to silts, and it's not applicable to clays. One thing that's really useful about relative density is that a lot of the engineering properties of soil relate to the soil's density. And so we can correlate a lot of useful parameters like soil shear strength, settlement properties, permeability, etc., to the relative density. So, with that being said, a couple of ranges that you might be interested in seeing. We typically have different descriptions to describe ranges of relative density. And so, for instance, if I have a soil that is between 65 to 85% relative density, we will often call this soil dense. Or if I have a very dense soil, that means that the soil is between 85 and 100% relative density. So this is nice because we don't have to use numbers, we just use descriptions when describing a soil. I can say I have a loose sand, or I have a very loose sand, or I have a medium sand, or a medium dense sand. Those kinds of things geotechnical engineers use all the time when communicating with one another. So folks, this is the end of the lecture. I appreciate your attention, and feel free to send me any comments or emails if you have any questions, and I'll be happy to address them. I hope you have a wonderful day, and I will look forward to seeing you later. Thanks.